Today, I will present a synthesis and open questions of the work that my collaborators and I are focusing and doing in the last couple of years in the Dinarics. And this work centers around intramountain basins and information that they're carrying about spherical processes which were affecting the late-stage evolution of the Dinaric Alps. And my talk today is structured around 3 points. So I will talk about tectono-sedimentary evolution of one intermountain basin of choice. Then I will give you an insight into regional, depositional, and tectonic trends. And finally, talk about the ways how we try to quantify tectonic signals based on the data we have from intermountain basins. The Dinarics, this is our Dinaric Alps. This is a orogenic belt which stretch parallel to the Adriatic Sea in the Balkan Peninsula. It is often referred as a south branch of the Alps. And this orogenic system resulted in a sequence of tectonic events during Phanerozoic, which are related to process of subduction and closure of one branch of Mesozoic Tethys Ocean. And today, the remnants of that ocean, as we see in this simplified geological map, can be visible along the center part of the Balkan Peninsula and are represented as different shades of green polygons. And this ocean in the past has been separating Europe, which was in an upper plate position and in this map shown in different shades of pink, and Adria, which at the time was in lower plate position, which was shown in different shades of gray. And since Cretaceous, when collision started, until Miocene, Pliocene times, the entire origin was affected by various magmatic phases. And what is interesting is that the magmatic products were more or less parallel to the origin, and they show youngening trends, and also the change of their composition, including more crustal material towards the foreland. And in addition, we also see thrust propagation towards the foreland and youngening of associated basins. And all this geological information led to previous authors, including us, to hypothesize that probably collisional process in the Dinarics was mainly affected by a process of retreat of the slab below the Dinarics. And towards the end of this collisional stage, during Oligocene and Miocene times, the entire Dinarics and their transition to the Alps and Carpathians, and of course, Pannonian domain were covered by intramountain, mostly lake systems, which are shown here as the orange polygons. And what we have to also take into account that already in the Miocene, around 20 million years ago, besides Dinaritic slab, which I just said was the main probably a mechanism driving the collisional evolution of the Dinarics, we have the introduction of Carpathian slab and probably the fact that it was retreated over the northeast left some traces in the Dinaritic lakes. Based on the current age constraints, we know that most of these lakes spread across the Dinarics were active between 18 and 30 million years ago. Based on paleontological data, these lakes are divided in 2 provinces, Dinaritic lake system. Those lakes are mostly located in external part of the Dinarics, and Serbian lake system located in internal part of the Dinarics. And in the following slides, I will briefly introduce the tectonic sedimentary architecture of Sarajevo-Zenica basin, which is representative of the Dinaritic lake system, and it is mostly located almost at the transition between these 2 systems. So the simplified map represents geological map of the wider area of Sarajevo-Zenica basin, where different colors represents different geological units. The striking feature here is this red line, which represents Busovača normal fault, which played a very important role in the basin evolution. And Sarajevo-Zenica basin is represented by this yellow polygon. Busovača fault is a normal fault which was reactivated thrust. Along this reactive normal faults, this led to exhumation of Paleozoic metamorphic rocks and growth of Bosnian-schist mountains along the southwestern margin of the basin. And in the immediate hanging wall of this fault, we have the deposition in Sarajevo-Zenica basin. The northeastern margin of the basin comprises of Mesozoic flysch deposits and Jurassic ophiolites. So this map here shows the distribution of major depositional units in Sarajevo-Zenica basin. As I said, Busovača fault was very important, and the general succession was divided in three parts. The oldest part, as we see here on this simplified stratigraphic column, is deposited during Oligocene and Lower Miocene times. And as we look at this map, today the remnants of these deposits we see mostly along the northeastern margin, and they're represented by light gray polygons. During lower to middle Miocene times, Busovača fault becomes active, and this fault is represented by different red lines, which represents the fault strengths. And coeval with activity of the fault, we have the position of major coarse grain succession, which is located mostly in the central part of the basin, and it is shown in this white polygon. And finally, during a late Miocene, based on the fact that youngest deposits, these late Miocene deposits, which are shown as dark gray patches, they're sealing Busovača fault. We assume that the fault was not active. So in the entire succession has been cross-cut by different faults, which resulted from different tectonic phase, mostly related to transpression, and these faults are mostly represented by dextral strike slip faults and associated faults here in this map shown as dark blue lines. So the oldest depositional sequence is characterized by radial clastics. So these are mostly deposits of fluvial system, braided rivers, conglomerates and sandstone channels, and bars, which are alternating in the vertical succession with mostly floodplain deposits with a lot of paleo soils, intercalations, and carbonate concretions. What is also interesting about this succession is that they are also associated with syn depositional reverse faulting, as in this image, and these faults, they show tectonic transport to the southwest, which corresponds to the major tectonic transport that we see in the thrusting phase during mountain building, probably suggesting that already during Miocene and maybe lowest Miocene times, we still have a mountain building process active. During lower mid-Miocene, the Busovača fault becomes active, and it is mostly, as I said, constrained along the southwestern basin margin, and leads to asymmetric architecture of this basin, dividing it into a more active margin along the south and west, and then more passive margin along the northeastern boundary of the basin. And in the northeast, we have mostly quiet deposition, which is represented by shallow water limestones, which often alternate with silts, clays, and coal deposits, in which we also find haraphyte fossils. In this 3D block represents our idea how the active margin looked like. So this margin and the position in this margin was controlled by normal faults, here represented by red lines, and along these faults, they allowed exhumation and growth of Bosnian-schist mountains and rejuvenation of the source, which supply basin with coarse grain sediments, which were deposited along the positional slopes, probably controlled by those faults. And the sediments, if we are on the field and if we stand at the location of this violet star, they are mostly thick coarse grain conglomerated sandstones, including big boulders of 2 to 3 meters. And going distally towards the more passive margin, of course, we don't see this direct association between faults and sediments anymore. How we try to reconstruct when was the The fault active is by this transition between shallow water carbonates and their association with thick organic-rich clay stones, which further develop in coarsening upward sequence, sometimes in a sequence of thick of 100 meters even. What is different here is that towards the end of faulting activity, the rate of sediment supply is higher than the rate of accommodation space was created. And this leads to dominantly progradational depositional trends in the basin. And this allows very powerful rivers and deltas to bring more coarse grain material deeper into the basin, as shown in these three graphs. And this is what we see in the basin as a very thick succession of fan deltas. This is geologists for a scale. They have rather steep forsets between 20 and 30 degrees incline towards the basin. And finally, during the late Miocene, deposition is still dominantly clastic, but finer grained with some coal intercalations. But unfortunately, the outcrop quality of this succession was not sufficient to do a detailed sedimentological analysis. So this brings me to a second point. So what we have learned from this tectono-sedimentary evolution from Saragossa Basin and how we can translate this to the region. So we could imagine that also the dinarites were developed through three phases during Oligocene and Miocene times, and then probably during latest Oligocene or early Miocene. Unfortunately, this succession in Saragossa Basin is still not dated. In probably certain parts of the dinarites, we still have the active mountain building process, probably the latest stage. And this tectonic phase, probably after 70 million years ago, it was replaced by a dominantly extensional tectonic event, and from late Miocene onwards, the dinarites were affected by transpersonal tectonics, which led to inversion and formation of many basins, especially in an external part of the dinarites. So the further detailed tectosedimentary analysis of other intramountain basins in the dinarites allow us to roughly estimate what was the extent of this extensional event. And here we see just a few folds suggested that the dominantly internal part of the dinarites were affected by extension, which reach external dinarites, Saragossa Basin, and Ponius Basin further to the west. And current idea is that probably this extension occurred in two phases, between 21 and 70 million years ago, and the younger phase with probably a peak around 40 million years ago. What is very interesting is the two phases corresponds to first phase with the onset of extension in Pannonian Basin, and second phase corresponds to actually peak of extension in Pannonian Basin. By looking at the depositional trends in these intramountain basins, I already said at the beginning that based on poor age constraints, probably they were active more or less in the same time. However, in several basins of the Dinaritic Lake system, like I show you in Saragossa Basin, but also in Banovic and Ugljevic, we also see older deposits, probably Oligocene, early Miocene. However, in lakes in the Dinaritic and Serbian lake system from 18 or 17 million years ago, the depositional environments and sequences are very similar. And they usually start with coarse grain alluvial clastics, reds, which are intercalated with shallow water limestones and some coals. And the entire system develops into, let's say, larger lake deposits, which is characterized by an increase of plastic inputs, but also we see now profundal lake facies as well. So we see different facies from fan delta deposits, microbiolites, oil shales, organic rich siliciclastitis, and so on. However, it seems that this, let's say, larger lake phase is it is actually not identical. By looking at the detailed sedimentary log in those lakes, it seems that somewhere around mid-Miocene, for the Dinaric lake system, we know that probably around 60 million years ago, certain basins, they record deposition more humid environment represented by coal successions, like in the Gatsko Basin. While in Serbian lake system, those lakes, they record basin-wide evaporitic successions, which are represented by sepiolites, magnesites, cerulezites, trona, shortite, and other evaporitic minerals. And these contrasting depositional environments in these two basin systems tell us that probably these two basin systems develop in contrasting also climatic conditions. For example, basins in internal part of the Dinarides likely develop in more arid climatic conditions, while basins in external part of the Dinarides likely develop in more humid climatic conditions. And this led us to hypothesis that during the evolution of this basin, the Dinarides were probably high enough to block moisture coming from the Adriatic Sea and actually leave basins in the internal part of the Dinarides in a rain shadow. And if this is true, this event didn't only lead to contrasting depositional environments and constantly climatic conditions, but also to speciation of different faunas on both sides of the mountain range. And potential drivers considering geological data are first option is actually previous and thrusting. This is actually thrusting, which is related to mountain building process. In that case, this would suggest that the Dinarides were high already in Oligocene. Second potential driver is a slab break-off of Dinaritic slab, which likely occurred somewhere between 30 and 20 million years ago. And in this process, we would expect that the isostatic rebound, which is associated with process of breaking off the slab, might significantly contribute to the topographic growth. And finally, recent work of Philip Alling suggests that the lamination of the mantle in the Dinarides might be responsible for a topographic uplift that he sees based on marine terraces in external Dinarides. And first we summarize actually, before testing all these hypotheses, we summarize the information that we have based on intramountain basins. When thinking about this mechanism, we would expect that this is a mechanism which causes the anomaly, which we see at the crustal level, which is long wavelength and symmetric based on the data that we have now. This mechanism should lead to switch from dominantly compressional to extensional regime and likely lead to topographic growth. And our first choice, or we started to examining slab break-off as a potential driver, which leads me to a final point of my talk, quantification of tectonic signal. To test this hypothesis, we run thermomechanical geodynamical models developed by Taras Geria. These models, they are based on different types of equations. They account for conservation of mass, momentum, and energy. And the model setup is inspired by geological evolution of the Dinarides. And in the upper right corner, this depth to distance profile is one snapshot of this model. Here, different colors, they represent different compositions. So different shades of gray are continental crust. Different shades of green represents oceanic crust. Sediments are brown. And we started the model with assumption that in Cretaceous we still had ocean and that oceanic lithosphere is around 80 million years old, and the entire system was closing by the push from the left, so from Adria. And in the following slide, I will briefly show you the main results of this modeling exercise. And so always on the left side, there will be a snapshot of this model evolution. And on the right side, this is a cumulative topographic evolution during the model evolution. And this snapshot represents onset of collision with further for the process of collision, this leads to a formation of thrusts which are propagating towards the foreland and thickening of the crust, which results in a mountain building process and topographic growth. And finally, with the slab break-off, this leads to isostatic rebound of the slab and also change in dominant stress from previously compressional to now extensional regime. But also what is interesting is that it also leads to a topographic growth up to 1 kilometer. And these numbers more or less fall within the range suggested by more general models focusing on slab break-off. And the sequence of events that I just explained more or less fit with the sequence of events that or this anomaly that we observe based on the field data. However, we still don't have much information about topographic growth and actually elevation of the Dinarites during Oligocene Miocene time. And this is something that we are going to do in the future. So the quantification of topography and testing hypothesis that the Dinarites were high enough during Oligocene Miocene time to affect these contrasting climate conditions and depositional conditions in the Dinarites is our next step, and which includes systematic dating of mostly lakes in the internal part of the Dinarites, oxygen isotope data, and revision of fauna. And with this, I would like to thank you for your attention.
Yes, thanks very much, Nevena.